Okay, folks, here we go. This is lecture 8.10. This is really the last of our lectures in the 8-bit part of the class. And I'll do a little bit more sort of quote lecture on Wednesday, and then we'll spend time doing a review. And I'm going to be assigning Lab 3 today, and then I'll tell you more about it on Wednesday. Now, let me just say a little bit about Lab 2. I announced this earlier on Moodle. I have gotten a number of sort of late-minute requests for more time on Lab 2 for various reasons, and you know we're still in the pandemic situation, so I'm happy to give more time. On the other hand, I don't want Lab 2 sort of piling up on us. We got to get Lab 3 out. So what I've done is I've changed the Moodle submission so that you can submit Lab 2 up until a week from today. Now hold on, you've got until Wednesday at noon, penalty free. So you've got another 2 days where you can submit Lab 2 if you need to, no penalty. After that, I do need to apply a 10% per day penalty. We do have to move on, and I want to get Lab 3 going. Okay, let's just say a little bit about dates going forward. So if you're in 231, you know that we have a midterm on Monday of next week. If you're going to need additional time on that midterm, let me know via email and we'll set that up. The exam is going to be 7 to 11 p.m. Eastern Daylight Time. We're now in Eastern Daylight Time. And it's going to be 2 hours. So it's going to be an entirely online exam. It'll be open book and notes. Use whatever resources you have available. Just don't collaborate with each other on it, and don't use Chegg. You can pick any 2-hour time slot to start the exam. So it'll open up at 7 p.m. It'll close at 11. Anywhere in that interval, you can start your exam. Okay. Lab 3, I'm going to assign today, and that's going to be due, if you're in 231, that's going to be due in 2 weeks. The question is, what is the structure and content of the exam exactly? Well, it's not completely written yet, but it's going to be about 20 questions. There'll be mostly multiple choice. Some will be fill in the blank. 25 problems. 25 short problems, mostly multiple choice, some fill in the answer. It'll all be on Moodle. So we'll take the whole thing on Moodle, and we'll get your
multiple choice.
Okay, more on that on Wednesday. And if you're in 297 CP, you're not taking the exam, of course. And for those folks, I'm making the Lab 3, which I'll talk about in a minute. That won't be due until a week later. And the reason is, for those folks who are in 297 CP, you've also got a deliverable in 304 coming up, and you need your breadboards and things for that. So I'm leaving this extra time to get this lab done. Okay. Lab 3. So what I want you to do is implement a distance measuring system using the sonar in your kit. So if you think about Lab 2, you made a digital thermometer. This device is going to be one that'll measure the distance to an object. I'll show you example codes for that. I'll show you how this thing works today, and we'll continue it on Wednesday. What you want to do is use it to measure object distance between 0 and 3 meters at 300 centimeters. And then you want to display the distance to the detected object in centimeters using your 4-digit 7-segment display, the one that you've been working on. And then in addition to that, I want you to have an LED blinking continuously. And the blinking of the LED is going to give an indication of the distance. And there's the specification. If it's greater than 2 meters away, you just want this LED that's blinking pretty slowly, 0.5 hertz. If it's less than 10 centimeters, it's blinking really fast, 25 hertz. And then in between 200 centimeters and 10 centimeters, you sort of draw a straight line between the distance and the blink rate. So that's the specification for the homework, for the lab assignment. And we'll We'll talk about the sonar at the end of class today, and then we'll talk more about this on Wednesday at the beginning of class. So I want to talk about a bit more advanced programming technique when you're doing microcontroller work. It's an important technique, and it's the distinction between polling versus interrupt. And so polling is what we've been doing all along, where we're sort of continuously waiting for something to happen. And we've got a loop. We're just waiting until some flag happens. We're waiting for something to happen. And we call that polling, where we just keep looking at a certain value to see when it changes. And not until it changes do we go forward. And to sort of illustrate this with a non-programming example, let's just suppose that sort of like a real life example. Suppose that you had some downtime and you and your friend planned you're going to watch TV together at your place, right? So this is a post-pandemic situation. It's you don't have to study, you don't have homeworks or labs, and you're actually going to watch TV. So on the left, this is a description of polling. This isn't what you do, but suppose your friend is going to come over, is going to come to your apartment, your house. So you sit down and you start watching TV, and you say, oh, wait a minute, my friend is going to come. I have to let them in. So do you go and stand at the door and wait at the door and wait and wait and wait? And you just sit there, you're waiting at the door for your friend to get there, right? You just keep waiting and you're not doing anything else. You're just waiting. Then your friend comes to the door, you say, hey, come on in. And then you sit down and you watch TV, and now you can spend the rest of the time just watching TV, right? The key is that you had to go and sort of poll at the door. You had to wait at the door before your friend got there, right? That's not what you would do. What you do instead is use an interrupt. So the first thing you do is you would tell your friend, hey, when you get here, just ring the doorbell. Knock on the door, ring the doorbell. And you're going to sit there and watch TV, right? You're sitting there watching TV, and you've got an arrangement with your friend that they know that when they get to your house, they ring the doorbell. You will get up from watching the TV, and you will go and let your friend in, and then you'll come back and watch TV together, right? This is called an interrupt. You interrupt what you're doing to go and let your friend in at the door, and the doorbell serves as an interrupt. And we're going to introduce that as a programming construct today. And it's very different from what we've been doing, where we're just sort of sitting there waiting. We're waiting for something to happen, waiting for this interrupt flag to occur, waiting. And we're not able to do anything else because we're waiting, right? What we want to do instead is build this interrupt. So that's what I'm going to show you here. And so I'm showing you this first with some pseudocode. This is not real code, but polling on the left and interrupt on the right. So look at the do loop we have there, or the while loop. So maybe we're gonna do something, whatever that instruction is, and we'll do something else. And now we're gonna just sit there and wait. We're gonna wait for a thing, whatever that means. And while we're waiting, the CPU is busy waiting. We can't do anything else while we're waiting. We're just sitting there, right? And our microcontroller can do nothing else while it's sitting there waiting for the thing to happen. Then when the thing happens, whenever wait for a thing equals 0, whatever that might mean, then we can go and we can do more stuff. So that's all the code that we've been looking at so far. That's called polling. Instead, what we're going to be looking at now is interrupt. And the idea is, first, we're going to issue a command that is going to enable the thing interrupt. And what that means is you're telling the microcontroller hardware, when you see the interrupt happen, when you hear the doorbell, right, then we want you to come down and execute the contents of this interrupt handling routine. And so interrupt whatever I happen to be doing, right? I'll be doing something, interrupt it, go down and deal with it with the interrupt handler, and then come back and let me continue with what I was doing. So now you're going to do stuff, you're going to do more stuff, do even more stuff, do more stuff, and then you're going to come back to the top again. And you're just going to keep on going through like this again and again and again. You're not stopping to wait for the interrupt. Rather, when the interrupt happens, when the doorbell rings, the processor will automatically break out from whatever it's doing, and it will execute the contents of this, what's called an interrupt vector. Once it's done, it'll come back up right where it was before interrupt, and it'll allow you to proceed. And so this makes a good use of the processor. So because instead of tying it up with a wait statement, like in the left side, the polling, you can keep doing things and it'll interrupt what you're doing to serve the interrupt. And you use this for things that tend to be time critical. You don't want to wait for them. You want something to happen, now. When someone comes to the doorbell and rings it, they want service now. So it's sort of analogous to that. So I'm going to show you a simple example. I'm going to blink an LED. And first, we're going to blink the LED with polling, and we're going to be using the timer that we've been looking at. And then in the next example, we'll show you the same thing with an interrupt. So this is the code for a 10 hertz LED blink. And let's just run through. This is sort of a review of last time we talked about timers and counters. We're going to have the LED on pin PB5. And so we're using the counter. First, we're preloading the counter with 0. Then we're configuring the counter to count up. This is called normal mode. It's going to count up, and it has a prescaler of 1024. I'll show you what that means in the bottom block. So that gets the counter. It gets the counter to start going. Then I misspoke. These two statements here, they are configuring. They're configuring the timer. And we're going to start the clock. Then we get into a while loop, and what's going to happen is we're first preloading the counter with this value, 65,536 minus 781. That's the appropriate value to get a 10 hertz blink rate. And I'll show you that. Let's sort of interrupt what we're doing and take a look at the timing. Why is it that that value gives us a 10 hertz blink rate? Well, when we say 10 hertz blink rate, what I want is something that's looking like this. And I want that to be 10 hertz, which means that I want this period here to be 0.1 second, which means I want half of that period, that's the delay, equals 0.05 seconds. And so what we're going to do is we're going to use the timer, the delay timer. It's going to count up 0.05 seconds. It's going to issue a flag. It's going to overflow. We'll wait for that flag, and then we'll toggle the LED. Okay, so why is it that this requirement translates to this preload value? Well, let me show you. I'm going to start out, when you're using the Explain mini board, the way we've been using it so far, it has a 16 megahertz clock. Each period of that clock corresponds to 0.0625 microseconds. So that's pretty fast. If you want to use a timer to get an LED that can blink at a rate that you can see, you really have to slow down that clock. So we use what's called the 1024 prescaler, which means it takes that 16 megahertz clock and it divides it down by 1024. So that means that every clock pulse that we feed into the timer is going to be 1024 times 0.0625 microseconds. That corresponds to 64 microseconds. Everything I'm going to be showing you today is going to be doing this. We're going to be using a 64 microseconds per clock cycle. Okay, we want it to blink at 10 hertz. That means that the period of the blinking is a tenth of a second, as I've shown on the right. So that means we want to set up a delay of 0.05 seconds. So I want a delay of 0.05 seconds. Each clock that we feed into the counter is 64 microseconds. So 0.05 seconds divided by 64 microseconds, 781.25 clocks. We're going to round that because we can't, these clocks don't have fractions of cycles. It's just going to count up a certain number of clock cycles. So we round it to 781. Now remember how this clock works. You preload it with a value, it'll start counting up. That's called the normal mode. And once it overflows, then it'll issue a flag and it'll go back to 0. So we want it to count 781 clocks. So we preload it with 65,536 minus 781. All right, why 65,536? It's a 16-bit counter. Okay, now let's look back up at the code up here. So we're gonna, in our while loop, we preload it with that value, and the counter is clocking. I mean, it's clocking away. So we just sit there and wait for it to overflow, and then once it overflows, we have to clear this overflow flag, and then we toggle the LED. I'll show you a little movie here so you can see how it works. So you can see that blinking. So that's what it looks like blinking at 10 hertz. And by the way, I'm using PB5. So I have both, I'm using both the internal LED and I hooked up an external LED because that's easier to see. So this is a way of simply getting a 10 hertz blinker with using the clock and using the approach that we talked about last time. Now, how could we do the same thing with an interrupt? I'll show you that on the next slide. Here it is. Okay, so I'm just rearranging this to use an interrupt. And so what I'm going to do is, well, we're setting up our output pin. I'm preloading the clock with the same value as before. And then these two commands are going to set the clock going in normal mode. They're initializing the clock. They set it going in the normal mode. They set it up to use this 1024 scalar, and then they start counting. Now, instead of waiting, I'm going to flip back a previous slide. I'm going to flip back. Instead of doing this, instead of waiting, that's polling. Instead of doing that, what we're doing is we have these two commands. These are sort of, the analogy was, you told your friend, hey, when you get here, ring the doorbell. You've got that agreement with your friend. These two commands are setting up the interrupt. The first one, TIMSK1, it's called a timer interrupt mask. Rather than going through and looking at all the details, I'm just going to give you examples of the code here. You can look in the textbook or you can look in the data sheet for the many, many details on this. But we're going to be, this is the command you would use that would enable the timer 1 interrupt. You also have to issue this command here, which is called global interrupt. That just allows interrupts to happen. And what this is saying to the AVR CPU is when you see, when the timer overflows, automatically trigger an interrupt. And when it does, come down and do this stuff here. And then when you're done, go back and continue executing where you were. So this was all done, notice, before the while loop. What do we have in the while loop? I have nothing. So all these statements up top were they were setting up the counter. We set it up to start counting. And then we had these two commands that I put into boxes that I say are analogous to you telling your friend, hey, ring the doorbell when you get here. We're telling the AVR, we're telling the compiler, we're going to use an interrupt. When the interrupt occurs, go down to this routine and handle it. And then we're just sitting there in that while loop. So this is not a particularly, we're not making good use of the fact that we're doing interrupt rather than polling. And what I mean by that is, let's go back to the previous slide. I'm going to jump back, right? In this one, which is now a mess because I've put all these circles on it. In our while loop, we have this while statement, and we're spending a lot of time in that while statement. And while we're waiting for that to happen, we can't do anything else. We can't sample any ADDs. We can't change any values. We can't check any push buttons. We can't do anything else while we're in that while loop. What we've done here is we've gotten rid of this waiting function here, right? While, because this is while, there's a semicolon at the end of this. I guess I need to clear that off so you can see it. Okay, this is the key. While we're waiting for that to overflow, right? This is a while loop, and the entire structure of the while loop after the condition is tested is this semicolon, meaning we just sit there and wait. We wait and wait and wait and wait for that overflow to occur. That's what that one statement will do. In the case of the interrupt, we've gotten rid of that. We still have a sort of a dummy wait right here, but we could be using this time, we could be using the resources here to do something else. I'll show you that in the next example. What I've done in this example compared to the previous one is where instead of waiting for the timer to overflow, we're causing that to happen with an interrupt. So whenever it overflows, it'll automatically come down here, preload the counter, toggle the LED, and then go back and do what it was doing previously. So it'll execute the same way. It's just going to cause an LED to blink. Okay, so why do you care, right? Why do we care? We've got this with we've done it with polling. We've done it with an interrupt. Why do we care? Well, let me show you an example of why you might care. Here's a program, and I call this LED blink ramp. This is one that's going to continuously change the frequency of an LED. And I'll go ahead and show you the movie. It's going to start out at a low frequency, and then it'll just keep getting higher and higher and higher. It's actually difficult to take a video of a rapidly blinking LED because of the limited frame rate of your camera. I had to set my camera at a 60 frame per second rate to see this. So this is something just to keep in mind looking ahead when you're doing Lab 3 and you're trying to take a video of a rapidly blinking LED. You may have trouble capturing the high frequency blink with fidelity because of the frame rate of your camera. Don't worry about it if you can't see it going really fast. But let me show you what's happening in this code. So first, this is all about setting up the interrupt. Then the actual useful code is in here. This is when I've got a command that says blinker of frequency. So it's a function that I wrote called blinker of frequency. What that's going to do is it's going to go and it's going to cause the LED to blink at a certain frequency. What's it going to do is it's actually going to come into this function here, and that only does one thing. It just chooses the preload value. That whole function just does that. It chooses the preload value, and then we come back into this loop here. And all I'm doing is I'm increasing the frequency by 1 hertz, and once it gets up above 30 hertz, I'm setting it back to 1. So this whole loop is just, all that does is it causes our frequency to increase from 1 to 30 and then back to 1. The action is taking place within this interrupt here. So we're setting up the timer to, when it overflows, go and have this interrupt handler service it. What that's going to do is it's going to load the counter with the value preload, and then it's going to toggle the LED. What is preload? Preload is the value that's determined by this function here. So this is getting a little tricky to understand and to explain now. But the point here is that we're able to do this. We're able to do useful stuff down here because we have not tied up the processor waiting for the timer to overflow. And because we're not waiting for it, we can do this kind of stuff. We can do other kinds of things with our CPU resource. All right, one sort of a subtle point that I have to make for you here is I have a statement here in a function. I have a function blinker, and I have this one statement here: preload equals 65,536 minus 7812 divided by frequency. When you're programming in C and you declare variables in a function, then those variables are only visible within that function. But here I have a variable that I want to be visible both in this function and in the interrupt handler here and in the main function. I want that variable to be visible in all of them. So what I'm doing is I'm declaring that variable up here. That's called a global variable. So when you declare a variable, I'm using a double. When you declare it outside of main, which you declare it up top, that makes it available to all the functions in the program. Okay, so I know I'm throwing a lot of tricky things at you right now. I'm gonna sort of make it worse before I can make it better. So I just wanted you to have seen, before you leave this, this 8-bit sort of lectures, I wanted you to have seen the difference between polling and interrupt. Now, a different topic. We're still on the topic of using the counter, but I want to show you how to use the counter to count external events, external things that are happening. All right, so for example, back to your friend coming over and ringing the doorbell. Suppose you wanted to count how many times the door to a room is open. You could put a sensor on the door, and you create some kind of a switch, and the switch is going to open and close every time the door opens. Suppose you wanted to use your MCU to count how many times that happened. Or another thing you might do is, suppose you created an infrared light beam, and every time someone walked across that beam, they would sort of make or break a connection. And you could configure a circuit that it's going to, have a transition between a high and a low value every time someone walks through the light beam. And that's an external event. And suppose you wanted to count those events using your clock. And so the topic I want to look at here is counting external events, right? So far, the work that we've done using the counter has made use of the internal clock. And every time the clock changes, it goes, from low to high, that ticks up the clock one notch, and the counter keeps counting up until it overflows. Now, instead of using the internal clock, we're going to use an external clock. And by we tend to think about an internal clock as a clock. Externally, we don't think about it as a clock. We would think about it as an external source or an external trigger. So here's the idea. Here's the counter that we've been looking at all along. This is our counter register. And when it overflows, it throws up this flag, and we're monitoring that. Now, the time base that we've been using here can come from an internal oscillator. And so we have our 16 megahertz clock. And in the example we just used, we have the 16 megahertz clock. We divided it by 1024, and we fed that in. And that was how we just did it. Alternatively, instead of doing that, we can use pin T0. T0 is actually a pin on the Atmega 328P, and here it is right here. It's this one that just showed up in red. PD4 also doubles as T0, which is this signal right here. And you can use that as a trigger for timer 0. And so the idea here is you can either set it up to trigger on the rising edge of T0 or on the falling edge of T0. And so the way you would do that, we have these registers that we use to configure the timer, TCCR0A and TCCR0B. That's timer counter control register 0A. This is timer 0 we're looking at. It's timer counter control register 0A and B. And when we set these at 00 and then 06 over here on the right, when we set it at 00, that just means normal mode, count up. And when we set it at 06, what we're doing here is we're setting these bits here, and these bits here are used to determine which of the many clock options we're using. And so if we set that at 06, at 110, that would mean it's got a value of 6. That would be choosing this one right here, which would mean that we're looking at T0, and on the falling edge of T0, that's this pin here, whenever we have a falling edge on that pin, that is going to clock our timer 0, and it's going to cause it to increase. So we can use the clock similar to the way we did before, the timer, but instead of counting internal clocks, we can use it to count external events. And every time we have this sort of this transition from high to low with a falling edge, we can capture that. And so I'll show you an example here. Sort of to try to make it interesting, I wanted to show you a simple application where we're just counting button presses. I've got just a button, and we ground that, and then this is on PD4, and we have the internal pull-up. So when our finger comes along and we press the button, what's going to happen is PD4 is going to go from high to low, and we're going to see this falling edge transition. And what I want to do here is every time we press this button, I want to see the number of times I press be reflected in a parallel bank of LEDs. Okay, now this is an 8-bit counter. This is timer 0. It's an 8-bit counter. And so what I want to do is I want to show the state of the counter between 0 and 255. I want to show that as a bank of 8 LEDs. Okay, so what's going to happen is when I reset this thing, as soon as I flash the code to it, all those LEDs will be off, and this device will just sit there and wait for me to come along with my finger and press the button. When I press the button, I will create this falling edge on PD4, also known as T0 for this application, and I should have a count of 7 zeros and a 1. Then when I press it again, the counter will go up to 2, and I should see that 2 reflected in my bank of LEDs. and so forth. And what will happen is every time I hit that switch, I should see these LEDs count up. So that's where I want to go with this. Let me just sort of skip ahead, show you the result, and then I'll show you how we got there. So this is the thing I'm building. I'm going to show you the little movie here. I've got a switch. It's a little bit obscured, but it's right here. And you'll see my finger press it. And every time I press it, you'll see the LEDs will start counting. 1, 2, 3, 4, 5, 6, 7, 8, so forth. So it's just counting up. And so it's an external event counter. The external event is my finger pressing on the switch. That's creating a downward going transition from high to low. And we're just causing the counter to count up. And then those LEDs are always showing me the current state of the counter. It's going to be a value between 0 and 255. And I think I keep this going until I have an overflow in the counter, I think. No, see if I can get the sound to work on this. Yeah, I was afraid that I wouldn't get the sound to work, so I'm having trouble getting the sound from my iPad to show up on Zoom. But that's why I'm actually put this demo on a bed. So every time I press the button, you can kind of see the circuit bounce. But anyway, you can sort of see what's going on. I just wanted to build an application where I've got an external event, my finger, and I'm counting up the clock. And then this bank of LEDs shows you the state of the clock. Okay, let me show you how I built this a piece at a time. Okay, so this is what we want to build. We want to build this device. How do you go about building it? Well, the very first thing, the initial step, before I get into the counter itself, I wanted to just wire up a device that's going to take. I'm using port D. That's PD0 through PD7. And I'm going to use that to drive a bank of 8 LEDs. Okay, so I have those 8 wires, the 8 resistors, the 8 LEDs. And I wanted to just make a simple program that would just test out the LEDs, right? And so here I got that. It'll just count internally. So I'm not using a counter yet. I'm not using a switch and an external event. I just wanted to make a very simple program here to test my wiring of the LEDs. Now, why did I do that? Anytime I sort of built this to give you sort of I wanted to show you how I go about building a system like this. If you're building something that's complicated, that has a number of pieces, what you want to do is build a piece of it, test it, even if it means writing a special piece of code just to test it. Build some, test some, build some, test some. So this thing that I'm building, this application that I'm building, I have to wire up a bunch of LEDs. I have to wire up a switch. I have to get a counter on there. I've got a number of different things that have to all work together. So I first wired it up here. Then I wanted to just make sure, okay, have I got the wiring correct? Will this thing count? So I just wrote a simple application here. And all it's doing is it's counting between 0 and 255. See, I have a counter. In my while loop, I have I++, then I'm sending I to port D, and then I'm just waiting, and then I'm looping again. So I starts out at 0, and it goes to 1, 2, 3, 4, 5, all the way up 254, 255, 256, and it'll roll over again to 0. And I'm just taking that value I, and I'm writing that to port D. And that's what's going to cause all these LEDs to blink. So I did this, mainly I wrote this code just because I wanted to test my wiring. But in doing it, I had this sort of aha moment. I said, uh-oh, I have a problem here. I can't use PD4, right, which is one of the pins on here, since I need that for T0, which is the edge trigger. right? This is another one of these many sort of contention issues that we have with the Atmega 328P. Let me back up, show you what I mean. Okay. Over here, we want to use, we want to do this whole business with this external counter. And I'm going to be using T0 right here. I'm going to be using T0 for my event counter. T0 is PD4. So for this application, I need to have that pin free so I can use it for the switch that I'm going to use and put my finger on it. That's my external trigger. And so when I first wired this up, I tested it, it all worked fine. But then I said, oh, wait a minute. I have the problem. I'm using PD4 in here, and I can't do that because I need to make that free. I have to reserve PD4 for the external switch that I'm going to use. So what I did is I came up with a workaround. I modified this code, and I came up with a workaround so that I would not use PD4. Okay, I'm going to back it up. Here, I'm using all of port D, right? That's PD0 through PD7. If I go forward, what I chose to do instead is use PD0 through 3, PD0 through PD3, and then I used PB0 through PB3. So I kind of split it up. I've got my 8 LEDs, but instead of using all of port D, I'm using the lower nibble, the lower 4 bits of port D and port B. And then I just had to write some code over here that would take the value I, and instead of just writing it all to port D, I'm writing it to the lower 4 bits of port B and the lower 4 bits of port B. So I won't go through all the detail here. You can look at that offline. But I had to do this so I could free up port D pin 4. And now here's the code that I use for this application that's going to have an external trigger, and it's going to count external events and display the result on a bank of LEDs. Okay, rather than me sort of going through all the code here, I've got it sort of well documented. I'm gonna let you look at that offline. I do want to say one thing about this application again here. So I'm going to show you this application again, and I want to see if you notice something peculiar that happens. So let's start counting. Okay, let me see if I can get the sound to work here. Give me a minute. There we go. Okay, so we got the sound, that little tick tick tick. Okay, so you can either listen to it, or you can also tell just by the position of the LEDs. But I want you to notice occasionally it's going to jump ahead a few steps. So when you count in binary, right, what we would expect is 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 1 0 0 0 0 0 0 1 0 0 0 0 0 0 0 1 1. I'm not going to do this 256 times, I promise you, but I wanted to, all right, etc. Now look what happens when I start counting. Okay, we got 1, 2, 3, 4, 6. Did you see that? I'm going to back it up. 1, 2, 3, 4, 6, 7, 8. It skipped 5. And what you'll notice is every once in a while, it will skip a position. Double bounce, that's correct. So do you know why this is happening? Remember, the triggering that we're looking for is going to be this downward going edge. Well, switches are not a problem. The question is, what specifically is happening in the switch, right? So, you know, what we've got in our switch is we have a pull up to +5, and we have our mechanical switch, and then that's grounded. And I'm tapping right here, and we're looking to see that line going from high to low. And every time that line goes from high to low, we have this negative edge. We're expecting to see a toggle, okay? So what's going to happen is if you looked at the voltage on an oscilloscope, which we don't have handy, right? You would see, let's suppose your finger is off the switch, it's going to be pulled high. Then as soon as you put your finger on the switch, you'd expect it to go to ground. And then you take your finger off the switch, it's going to go high again. Put your finger on the switch, it's going to go to ground, right? So this is what we expect to happen. These would be our button presses. So I have one there, and I have another one there. What actually happens inside the switch is there's mechanical bounce. The switch is actually made up of pieces of metal. You know, there's one piece of metal here and another piece of metal here. And when you put your big finger on there, you know, let's see if I can draw a finger, right? Fingernail. When you put it on there, you're causing these two pieces of metal to come together. But what actually happens is they come together and then they bounce apart, come together and they bounce apart, come together and they bounce apart. And this whole thing happens back and forth. Anytime you take two pieces of material and you sort of slap them together, they will bounce apart. It's a very small amount of bounce, but what happens is it will back over to sort of our pseudo oscilloscope drawing here. What'll happen is it will come apart and then it'll bounce down again. And you're going to get these artifact bounces. That's called switch bounce. And this is something that occurs with mechanical switches, and it plagues edge-triggered systems like this. And it happens because you don't expect this to happen. You figure when your finger pushes that switch, you're causing those two metal contacts to come together, right? But these are pieces of material, right? Ask your mechanical engineer friends what's going to happen. As soon as you push them together, they will mechanically separate, and then they'll come together again and separate. And that whole process will be oscillating. Eventually, it'll die out. But every time they come apart and then come back together, it actually creates another transition. It's not related to how long I'm holding the switch. This happens as soon as I strike that switch. So it's a transitional switch bounce problem that you have. And there are things that you can do to debounce a switch. I'm not going to talk about it here. But if you ever are encountering this, tuck this idea away that you have switch bounce. It's when you have a mechanical switch and you're looking at an edge, you know, transition, you will encounter switch bounce and you'll have to deal with it. So just sort of tuck that in your mind and be aware of it. Okay, I'm going to show you now another application of the timer. All right, so I'm sort of staying on timers, but here's yet another application. And this is continuing with the idea of measuring external events. All right. There's a unit on the timer. We're going to use timer 1 here, the 16-bit timer. It's called the input capture unit. All right. We just looked at edge triggering that, but there's another device called the input capture unit. And what you can do is you can use it to measure how long it takes until you see that edge, like in what I just showed you, right? You know, I just showed you my finger was pressing the button and that was creating an edge. The input capture unit will measure how long it took to get to that edge. You can also use this to measure pulse width. And so here's the idea. Let's sort of look at the top half of this. So suppose that my finger created this falling edge right here. Well, what you do is you'll start this clock counting, right? You'll set it to go. You tell it to issue a flag when it detects a falling edge. And it's going to start counting until it gets that edge. And as soon as it gets that falling edge, it's going to set a flag called ICF1. It's the input capture flag. 1 stands for timer 1. So what we're going to be doing is polling this, this register TIFR1. That's the timer interrupt flag register. And what we're going to do is write some code that once we get that flag, we're going to just ask how many clock cycles elapsed between when we started this and when we saw this edge. Right? You can also do the same thing on the rising edge just by configuring it a little differently. So I'm going to show you an example of that, and to try to make it kind of fun, it's a sort of a switch timer game here. And so here's a simple application. What I've got is I'm going to have an LED that's going to turn on, right? And as soon as the LED glows, I want to press the switch, and I just want to see how quickly I can press the switch. So that's the application I'm going to show you. Well, actually, I'll before I show you the code, let me show you the movie. Okay, so jump ahead. Here's how we do it. But here it is. So I'm going to set this up, and as soon as the LED glows, I want to press that switch, and I'm going to measure how long it took, first in clock cycles and then in converting that to seconds, how long it took for me to actually press that switch. I'm sort of measuring my reflexes here. So let's get this going. Now the news is on in the background, so you can hear that, right? And these numbers here show how long it took. Now I'm going to start really paying attention. I'm going to try to get it fast, right? Wait a minute here. Okay, 0.2, 0.29, 0.24. I'm trying to get it as fast as I can. As soon as I see that thing come out, I'm trying to hit that switch. All right, we can stop it there. Now, a question for you. I'll stop it because the news in the background is distracting. But this is when I was really paying attention here, and I was trying to hit that as fast as I can. And you may wonder, sort of you're measuring your eye, brain, hand reflex here. As soon as you see an LED and you press a switch, how long do you think it takes? How much time elapses? And what I found is it's about 0.3 of a second for me between when I see the LED and when this device is registering that I've hit the switch. Okay, so this was it was sort of an example of yes, it's a reaction time of 300 milliseconds. Now that's the time it took for me to register that the LED was on. I had my finger positioned and I had to press the buttons. Yeah, so that was my reaction time. Okay, how do we build this? Well, the first thing we do is we're going to initialize timer counter control register 1A. For normal mode. That means we give it all zeros, and all that's going to do is it's going to tell it to count up when you get a clock. I'm going to turn on the LED, which is a signal for me to go. I'm going to clear the counter register. Then this next line, when I'm setting up timer counter control register 1B, that really starts the counting. So once it gets that, it starts counting. And then I just monitor this flag until I see the flag come up, the ICF1 flag, and that says we have detected a negative edge. All right. So now I stop counting and I say, well, what is the state of the counter? How many clock cycles have elapsed? I know the clock that I've provided, and that'll tell me how long it's been. And so here's all the code. Let me just give it to you without going into it all in detail here. Okay. Now, let me just make this remark. I'm throwing a lot of TCCR1, TCCR1B, and all this kind of stuff at you. I don't expect you to have a full working memory and knowledge of all of this kind of stuff. I'm showing you some examples. This is really just a few of the capabilities that you can get out of the timer. And I wanted you to see some of the examples and some of the way they're used. If you ever have to actually build a timer, you can use some of the codes that we've got here as building blocks, but then you're going to have to go and get a source of information to study it up and see all the different modes. You can look at the examples that are in the textbook, or you can look at the data sheet to really find out all the different modes. So I just sort of give this to you as an example of one mode that you can use with these counters. Okay. I want to show you one more thing you can do. You can use this the same capability to measure the pulse width. So previously, what we did is we measured the time to an edge, right? I started here and I measured how long it took to get to a falling edge. Another way you can do it is suppose that you have a pulse like shown here, and I want to know how wide is that pulse, right? Why do we care how wide a pulse is? We'll get to that in a minute. The way you do it is you'd set it to trigger on a rising edge. You start the clock and you see how many clock cycles elapse here, right? Number of cycles to rising edge. Okay. Then once you have that, you'll restart the clock and you'll measure number of cycles to falling edge. And the difference between those is the number of clock cycles that exist between the rising edge and the falling edge. Okay. I won't go through all these details, but I'll just show you an example of how we're going to use that. And we're going to use that as the code for making the ultrasonic distance sensor work. So you have this sensor in your kit. Now I'm gonna guess that a fair number of you have already used this ultrasonic distance sensor in conjunction with an Arduino. Send me, if you've done that before, let me know via chat. Who has used this? Who has used this sonar before via Arduino? Anybody? Does Tetrix count? I'm not sure. I'm not sure I even know what Tetrix is. All right, yeah, I know that at least a few of you have done this with an Arduino, with robotics kit and things like that. I'm gonna guess that none of you have actually looked at how do you code that using a device, a microcontroller like we're using, although maybe Kobe has on another micro. Okay. So I want to show you how to program that using what we just talked about. So first of all, how does this device work, this sonar work? This is a device that's used to measure the distance to an object. And so what it's got is there's a T, that's for transmitter. Transmitter here, and then a receiver here, okay? T and R, TX for transmit, RX for receive. And so what happens is the transmitter is going to issue a pulse of sound, but it's at a frequency that we can't hear. I think it's 40 kilohertz, so it's above the frequency that we can hear, and it comes out of that transmitter can. It's like a speaker. You know, we talked about how the piezoelectric speaker works. It's similar to that, and it sends that pulse out, and then it'll travel out away from the transmitter at the speed of sound, right? And the speed of sound is 343 meters per second. Or I'm also showing you it's 34,300 centimeters per second. So what it's doing is it's sending out this little burst of sound wave, a short duration burst, and that travels out until it encounters an object. Then it'll bounce off the object, and that echo will come back, and it'll be detected by the receiver. Okay, now you've experienced echoes before. You know, you go and you stand in front of a wall and you say, hello. A little while later, the hello comes back, right? And you may know that you can count how many seconds it takes from when you say hello and when you get that echo back, and that'll tell you how far away that obstacle was, because, you know, the sound is traveling at 343 meters per second, right? So this ultrasonic device does the same thing, although it's at a frequency we can't hear. It's ultrasound. And so let me show you how the way the device works and how we interact with it. So the first thing is that there are 4 pins on this sonar. There's VCC, which is 5 volts. There's ground, right? We know what that is. Then there's a pin called trigger. And there's a pin called echo. And so what we have to do is we have to provide this device with a 10 microsecond duration trigger. So we have to give it this. We have to go high and then low, 10 microseconds. And that's very easy to do. I mean, you just have to, you know, set a pin high, wait 10 microseconds, and then set it low. And then once we've triggered the device will generate this relatively short duration high frequency pulse of sound. So it's 40 kilohertz. And I don't remember offhand the duration of that pulse, but that gets generated by the transmitter and it travels out. And eventually it will encounter an object and it will come back, right? It bounces off the object and then it returns and is detected by the receiver. And there's a time delay if you look at this transmitted waveform and the received waveform, right? The delay time is equal to twice the range divided by the speed of sound, right? Because the time delay is the time it takes for that pulse to go out, turn around, and come back. So the distance traveled is 2r, and it's traveling at the speed of sound. So that time delay is 2r divided by the speed of sound. And what the ultrasound sensor does inside its receiver is it puts out a pulse on this echo line. And it's a pulse that's going to go high the instant it transmits, and it's going to go low the instant it receives. And so what we do is we monitor this echo line. And by monitoring the echo line and in determining its duration, we can determine how far away our object was. Okay? Because so what we're going to do is we're going to measure the width of the echo pulse using the technique I just mentioned, right? And then based on that, we can determine how far away our object was by just inverting, this relationship, right? The echo, the width of the pulse is twice the range divided by the speed of sound. So we can use this to very easily determine how far away our object is. Okay, so how do we do it? Well, we're going to use the technique we just looked at here of measuring pulse width. There's all of this stuff in here having to do with setting things up, waiting for a rising edge, waiting for a falling edge, and measure delays. Okay, and so let me just show you how we do it step by step. How do we create the trigger? We just have to create a 10 microsecond pulse to trigger the sonar. Then we measure the echo. And to measure the echo, what we're doing is we're measuring the width of the echo pulse. And that's all of these steps in here. I won't go through all those in detail, but we finally get the result, convert it to distance, and we print it out, and then we repeat. So this is what our code is going to look like. Okay, this is the code. Let me just show you a little tiny bit of it. I'll just show you these lines here. All this does is it generates our 10 microsecond trigger. Okay, I've got a question. Is when going farther, is it better to have a longer or a shorter pulse? Well, fundamentally, what happens with a device like a sonar or a ranger is what matters is the energy in the transmit pulse. And because you have to talk about the signal to noise ratio. The signal is the echo that you're getting from a target, and then noise is unwanted signals that are generated in the receiver itself. And so you can see far if you have a strong signal to noise ratio. And what happens is the farther an object is away, the weaker the received power is going to be. And that's because, when you transmit that waveform, that sound waveform, it doesn't just transmit in a straight line. It kind of flares out as it transmits. What I mean is you've got your transmitter. It sort of looks like a can here, right? And it's emitting these sound waves. But what happens is, sort of like a flashlight beam, they spread over a larger and larger and larger space as you get farther away. Think about, if you take a flashlight beam and you shine that on the ground at an oblique angle, you'll see that beam getting wider and wider and wider as you get farther away. And the same thing happens with our sound waves. So our sound spreads out farther and farther and farther. And so an object that's close in is going to see a stronger incident power density than an object that's farther away. And so the object that's farther away is going to have a lower signal to noise ratio than the object that's close in. What matters here is the amount of energy in the transmit pulse. So how do you get a lot of energy in the pulse? You either make it tall, it has a big amplitude, or you make it long. You know, if you have a pulse that's long, it can have more energy in it. And this sort of gets into various kinds of trade-offs. You have to look at what's the resolution, how complicated is the transmitter and the receiver. I don't want to get too distracted going on about this, but the little device that you have is a is a $3 sonar. It's the sort of the simplest, cheapest little sonar that's around. And I'll show you what that looks like when we put it in an example. So I won't go. I'm giving you the code here to run it, okay? And displaying it on the COM port, and I'm going to show you a demo of it. All right. So what I've got is the sonar is sitting here, and I'm looking at it from behind, and I've got it positioned in front of a wall, and I've got a camera behind it, and I'm going to show you what it looks like when I start to put some objects in front of this thing. So let's see, what's the question here? The transmission length is equal to the trigger input length. Now, here's what matters here. So if we look at the timing, we're always going to give it a 10 microsecond trigger. That'll always happen. And then the transmitter will issue this pulse. It's going to travel out, bounce off of an object, and come back. And the delay time here, this delay time will depend on the range to the target. So if the target is closer in, this echo will come in sooner. If the target's farther away, the echo will come in later. And so what happens is we're going to be monitoring this echo pin. It would look like this if the target is close. It will look like this if the target is sort of, let me change colors here. It would look like this if the target is at an intermediate range. And if the target is even farther away, it's going to sort of look like this. So the receiver of this device is going to be putting out a pulse of variable width, and it's on the echo line. And the width of that pulse is directly proportional to the target range. So what we have to do is build code using what we've just talked about to just measure the width of that pulse. And we want to know how long does it take between the rising edge and the falling edge. So we'll measure that, and it could be small, it could be medium, or it could be large. And then we're going to convert that into target range. All right, what's it look like when you run it? I'm going to show you a display with a lot of information. So I'm going to show you a little movie, and I've got, this is my, this is my COM port display, right? And I'm going to update this 4 times a second. And what I'm going to show is every quarter second, I'm going to show a row of numbers. And so the first row on there is going to be how many clocks it took to find the rising edge of that echo pulse. Then how many clocks it took to find the falling edge. And then the number of clock pulses in between those. So it's the difference between one and the other. Now, I'm using my 16 megahertz crystal with a divider of 1024. So that means each clock pulse has a duration of 64 microseconds. And so I know, let's say I've got a number of, let's say 96 clocks between the rising edge and falling edge. So I've set it up to measure that, and I've found that I have 96 clocks. That's how long, it took for the timer to first find the rising edge and then find the falling edge, and that's the difference, okay? And I know that I have 64 microseconds per clock. Okay, so I have 64 times 10 to the minus 6 times 96 is 6.144 times 10 to the minus 3 seconds. So that's what that's telling me, right? I'm looking at something, some object, and the round trip travel time is 6.144 milliseconds. That's how long it took for that sound signal to go out and then come back. Okay. Now, the distance, let's see, the time delay between transmitting and receiving is twice the range divided by the speed of sound. What did we say the speed of sound was? I have to go back and look at it again. 343. It's 34300 centimeters per second. Okay, and that is equal to 6.144 times 10 to the minus 3 seconds. And so I should be able to take all of this and solve for R. So I take that delay of 6.144 times 10 to the minus 3, multiply it by 34300 centimeters per second, divide by 2, and I end up with 105 centimeters away. And if you come back and look at this line over here, I've got the number 105.4. Okay, so I'm kind of glad that worked out. Now, all of this that I've just showed you here is also described here in the code. Let's see, it's described up at the top, right? Everything that I just described is also described up here in the comments at the top. So when I set this movie to running, you're going to see the number of clocks until the first edge, the number of clocks until the second edge, the difference, the total number of clocks between the edges. That's the width of our echo pulse in clocks. Then I'm converting that to a distance in centimeters and in inches. Okay, so that's what we're going to be showing. Now, when we're looking at the movie, really just pay attention to the very last line, the last two, the distance in centimeters or the distance in inches, depending on which one you're more comfortable with. Ignore when I'm showing you this because there's a lot of information at you. Ignore all of these lines. You can look at those sort of later on if you want. Okay. Okay, I'm going to show you the movie. It's set up in a room. I'm in a guest room at my parents' house right now, and I've set this thing up and I've got it running, and it's set up on a little table. I've got the camera behind the sonar, and I let it running for a while, and I'm staring at a wall. And what you can see here is just, you know, the numbers 41.9. That's 41.9 inches between the sonar and the wall. So that's what it's looking at when I turn this on. Okay. Now I bring my trash can in front, and you can see it's 2.3, 3.4. This is the number of inches away. I'm moving the thing farther away. Okay. I'm going to stop it here. It jumped up to 160, 162, 165. There's this number here that shows up occasionally. I don't know what causes that. I'm working on it to figure that out. So there is this sort of glitch that shows up from time to time. There are two sort of glitches that shows up. One I can explain to you. The other one I can't explain yet. But the important thing was when we started this, we had 41.5 or 41.9. Excuse me. Inches. That was the distance to the wall. Then I brought up this trash can. Oh, but now, by the way, let me tell you about this trash can. So I said I'm staying with my parents. I'm helping my parents with their recovery from COVID right now. So I've been spending a lot of time there, And I'm in a guest room at their house. That accounts for this colorful material. This is the trash can that I had when I was a kid, because my parents don't throw away anything. So when I was like 10, I had this very trash can in my room. So this is about 48 years old, this trash can. Anyway, that's why I'm using that as a convenient target from here. But you can see when I introduce the trash can, it's only 3 inches away, and I bring it close, and then I bring it farther away, and that's what we're looking at here. Okay, I'll keep bringing it farther away, and you can see that the distance is increasing. Okay, down here. Now we're back to the wall. Here's my hand, a few inches, bring it farther away. Now I want to show you what happens when I come along and I cover up the sonar. All right, that's one glitch. When it doesn't get a signal, when you cover up either the transmitter or a receiver, it'll always show you 471 something inches. That's because it's sort of reaching the end of its own internal count, and it's just putting out this number that's consistently a pulse of 1,092 or 93 clocks. That's what happens if it doesn't get an echo back. It sort of reaches its own maximum count, and that's the source of that pretty consistent sort of glitch you get when you deliberately cover it up. So I'd say, having hooked this up, I understand it fairly well, with the exception that occasionally I will get this other strange number. Okay, I'm going to stop it here. I'm going to get rid of all the markings here and come back to it. Okay, so here, you see those numbers here, the 472, that's with my finger covering it. Okay, now I'm just using my hand, moving my hand away. Okay, we got a 43.7. That's when it was seeing the wall. Right. So sometimes it's seeing my hand, sometimes it's seeing my wall, seeing the wall. Inside a crowded room is actually a tricky environment for something like this, one of these devices. Ideally, what you do is you would sort of deploy it someplace where there's not a lot of obstacles around, where you're not going to get multiple sources of echo. And so in 304, for those of you who are in 297 CP, you're using this device to measure people coming in and out of a room. So you would install this sort of at the door jamb up on top of a door, sort of looking, into the room. And you should be able to deploy it there where you're not getting a lot of extraneous echoes. Here, I'm kind of in a small room tucked into a corner here, and I do have a number of sources of unwanted echo. I get a bounce off of this wall here. Sometimes I wonder if I'm getting some echo off of this wall. There's actually some other sort of stuff over here that I couldn't move around. So this is a bit of a tricky environment to be operating this, but nevertheless, you can sort of see how it works. It's able to just measure the distance away to an object, and it does a pretty good job. Okay, so what I want you to do for lab 3 is build this device, hook it up to your 4-digit 7-segment display, and also get that blinking LED. And you're going to be making use of many of the things that I just talked about today. Now, I plan to say more about the sonar and some of the particulars of that lab in class on Wednesday. Okay, we're at the end of the hour. Any questions or comments?
I just looked through my lab kit and I couldn't find the sonar sensor, and I looked online and I also couldn't find. Would I have to get that one off like the SparkFun website?
Oh. What course are you in? Are you in 231 or?
I'm in 231.
Okay, I'm going to I'm going to bring up the. So you should have my screen there.
Yeah.
I'm going to bring up the parts list for 231. Yeah, so you should have an ultrasound sensor in your kit. Right? Everyone should have one in their 231 kit. So I mean, I would, and that's a pretty big box that you've got, right? I would look in there, 4 times, and if you
Okay.
don't have it,